All right, welcome to the Explainer. Today we're going to tackle a classic brain teaser. But this isn't just any riddle. It's actually a foundational problem in artificial intelligence, and by figuring it out, we're going to see exactly how a machine thinks its way through a complex logical puzzle, step by perfect step. Okay, so here's the setup. You've got 3 missionaries, 3 countables, and 1 little boat that can only hold 1 or 2 people. The goal seems simple enough, right? Get everybody to the other side. But here's the catch, and it's a big one. At no point on either side of the river can the cannibals outnumber the missionaries. If they do, well, let's just say it's bad news for the missionaries.
But like I said, this is way more than just a brain teaser you'd tell around a campfire. It's a really famous problem in AI, and it was first formally studied way back in 1968 by a guy named Saul Omerel. It's basically the perfect example of how you can take a tricky, kind of abstract puzzle and translate it into a language that a computer can understand and then solve perfectly.
So before we can just let an AI loose on this thing, we have to do what the AI itself would need us to do first. We have to break down the rules of the game perfectly.
Okay, so everything, and I mean everything, hinges on this one critical rule. A valid state, or a safe situation, is any time the missionaries are either equal to or outnumber the cannibals on a riverbank. That's the safe zone. But the second the cannibals have the majority, even for a moment, that state becomes invalid. And that is the one rule the AI absolutely cannot ever break.
So think about it. How would you solve this? Most of us would probably use trial and error. Maybe move some coins around on a table, and we'd probably mess up a few times. But a computer? It can't just try things randomly. It needs a completely structured step-by-step process to guarantee it finds a solution, and not just any solution, but the best one, all without ever breaking that main rule.
And that process, it all starts with defining the problem in a way the machine can understand. And AI needs every little piece of the puzzle laid out for it, super precisely and super structured.
So to do that, we have to define 3 key things. First up is the initial state. Think of it as just a snapshot of the very beginning of the problem. So for us, that's simple. 3 missionaries, 3 cannibals, and the boat all chilling on bank number 1.
Okay, next up, we have to define the actions. These are all the possible legal moves the AI can make. The boat can take 1 missionary across or 2 missionaries. It can take 1 cannibal or 2 cannibals. Or it can take 1 of each. That's it. That's the entire playbook. Just those 5 moves. And last but not least, we give the AI a goal test. This is basically the finish line. The computer knows it has won the game when there are 0 missionaries and 0 cannibals left on that starting bank. Everybody's on the other side. Now this is where it gets really cool. When you take that initial state and you combine it with all the possible actions, and then all the situations those actions can lead to, you create something called the state space. Think of it like a giant map of the entire problem. It shows every single possible legal configuration of people and the boat. It's the whole world that the AI is allowed to explore.
All right, so the map is drawn. Now the AI can actually start searching for a solution. This is where the real work begins.
And the computer doesn't just wander around this map randomly. It uses a special algorithm to build what's called a search tree. It starts at the root of the tree, which is our initial state, and then it branches out. Each branch is a possible move, and this creates a huge tree of all the possible ways the puzzle could unfold.
For this, we're going to use a classic algorithm called breadth first search, or BFS for short. The best way to think about it is like ripples in a pond. It starts at the center and explores everything that's just 1 step away. Then it explores everything that's 2 steps away, then 3, and so on. It checks out the entire search tree level by level, so it absolutely doesn't miss a single possibility.
So why go with BFS? What makes it so good for this? Well, it gives us 2 massive guarantees. First, it's what we call complete. That means if a solution exists at all, BFS is guaranteed to find it, no question. And second, it's optimal. That means it won't just find any solution, it'll find the one with the fewest number of steps, the shortest path.
And here's the really smart part. This is how the algorithm deals with that one big rule we talked about. At every single move it considers, it asks one question. Does this move lead to a situation where the cannibals outnumber the missionaries? If the answer is yes, it just stops. It prunes that entire branch of the search tree. It completely ignores that path and everything that would come after it. That's how it guarantees it never, ever breaks the rule.
So after all that searching and pruning away the bad moves, BFS finds the single optimal path, and it takes exactly 11 steps. Let's walk through it. First, 2 cannibals cross. Then one of them brings the boat back. Next, the remaining 2 cannibals cross, and again, one returns with the boat. So far, so good. No rules broken. Now 2 missionaries make the trip over. But someone has to bring the boat back. And this next move is the really clever one, the one most people miss. 1 missionary and 1 cannibal get in the boat and return together. This is the key to rebalancing everything.
Okay, now that we have 2 missionaries on the far side, the last 2 missionaries can finally cross over. Now all 3 are safely on the goal bank. And from here on out, it's pretty much a cakewalk. It just turns into a little ferry service for the cannibals. 1 cannibal goes back to get the boat, picks up another one, and they both cross. Then 1 returns for the final cannibal, and then the last 2 cross together. Boom! Everyone is safe on the other side. Goal complete, in a perfect 11-step.
Okay, so it's a fun puzzle, right? But what does solving it really teach us about the power of AI and search algorithms?
Well, this one little puzzle actually teaches us 4 really fundamental concepts in AI. First, there's state representation. You have to be able to turn a story into data. Second, constraint handling. An AI has to follow the rules, period. Third, systematic exploration. A methodical search is way more powerful than just guessing. And finally, the whole idea of the state space, realizing that you can actually map out these incredibly complex problems and then navigate them.
All right, now let's take this from a so-called toy problem to the real world. Because believe it or not, the exact same logic that solves this little riddle is powering technology you probably use every single day.
I mean, this logic is absolutely everywhere. You know, when Google Maps or Waze finds you the fastest route home, avoiding all that traffic, that's a massive state space search problem. When one of those robots in an Amazon warehouse navigates the aisles to get your package, it's doing the exact same thing. It's how we design complex computer chips, how we figure out the best sequence for a factory assembly line. Even how Google's crawlers search the entire web is based on this fundamental principle. Define your starting point, define your possible moves, and then search for the best path to your goal.
So you see, the Missionaries and Cannibals Problem, it's more than just a cute puzzle. It's a perfect small-scale proof of concept. It shows us how a simple, systematic algorithm can find a beautiful, elegant solution to a problem where a human might just get frustrated and give up. And that leaves us with a really powerful final question. If a simple algorithm can solve this puzzle so perfectly, what happens when we apply that same kind of systematic, computational power to the truly massive, complicated problems facing our world? The potential is just staggering.